A mysterious planet has captured the attention of analysts and space enthusiasts alike. Recently, the James Webb Space Telescope, JWST, revealed the clearest image of Proxima ever captured, raising intriguing questions about this distant world. What secrets does this far-off planet hold? Could it support life? Let's delve into what the JWST has uncovered. Stretching billions of years into the universe's history, we can begin to grasp how systems formed. With the James Webb Space Telescope, scientists can take this understanding to the next level, exploring the farthest reaches of space. The infrared images captured by JWST are unlike anything our natural eyes have ever seen. Its advanced capabilities, akin to a sophisticated camera, allow astronomers to focus on the early universe and gain a deeper understanding of the formation of stars, planets, and galaxies. By analyzing the data from these images, astronomers can separate the various light frequencies, allowing them to study specific elements within distant objects. JWST doesn't just stop at observing stars. It also aims to investigate the atmospheres of exoplanets, searching for signs of extraterrestrial life. Its ability to look farther back in time and space than ever before has led to groundbreaking discoveries. For example, scientists have used JWST to detect more mass than previously believed to exist in the universe, hidden within massive galaxies. One of the most significant revelations came in 2013 when astronomers discovered hints of a gravitational pull exerted by a planet on Proxima Centauri, our closest neighboring star system after the Sun. Following years of observation, this planet, orbiting Proxima Centauri, was eventually named Proxima B. This discovery is particularly exciting because Proxima Centauri is just 25 light-years away, making it one of the closest exoplanets ever found. However, don't let its proximity fool you. Proxima B is an entirely different world from Earth. The planet is about 30% larger than Earth, meaning it is bigger in size. But what's most striking is its orbit. Proxima B completes 1 year around its star in just 11.2 Earth days. This places it extremely close to Proxima Centauri, at a mere 7.3 million kilometers away, about 5% of the distance between Earth and the Sun. You might assume that such a close proximity would make the planet unbearably hot, but Proxima Centauri is a small, red dwarf star that emits significantly less energy than our Sun. From Proxima B's surface, Proxima Centauri would appear as a dim, red orb, about twice the size of our Sun. If Proxima B is indeed in its star's habitable zone, there could be the potential for liquid water, a key ingredient for life. However, before we start packing our bags for an interplanetary adventure, it's important to realize that Proxima B is far from being a second Earth. The planet is tidally locked, meaning one side always faces its star while the other remains in constant darkness. This makes for a harsh and extreme environment, where the side facing the star would be subjected to intense heat and radiation, while the dark side would likely be freezing cold. This results in conditions that would be highly unfavorable for any potential life. Furthermore, if a planet is too far from its star, it won't receive enough energy, causing water to freeze, making it uninhabitable. Proxima Centauri, despite being smaller and less massive than our Sun, has its own set of challenges. Its relatively weak nuclear fusion core sits much closer to the surface, leading to turbulent and violent surface activity. This generates intense, strong magnetic fields that produce high-energy radiation and particle impacts, posing significant risks to planets like Proxima B that orbit within its habitable zone. While scientists had some knowledge about magnetic fields around neighboring stars, they were previously in the dark about the specific conditions around Proxima Centauri. Recent surveys using high-resolution magnetic field maps have shed light on this. These studies revealed that Proxima B is bombarded with solar wind radiation, about 10 times more than Earth, posing a grave threat to any potential life. A solar flare from Proxima Centauri, like the one in April 2021, was many times more intense than any flare ever seen from the Sun. It's hard to imagine life surviving under such extreme radiation without specialized protection. While the idea of a habitable planet around Proxima Centauri is exciting, reality paints a much more challenging picture. As humans, we've long been fascinated by the possibility of encountering extraterrestrial life. In late 2020, That curiosity reached new heights when an unusual signal was detected coming from the Alpha Centauri system. This signal, which appeared at a unique frequency of 9,827 MHz, unrelated to any Earth-based satellites or broadcasts, sparked speculation. Some experts suggest that it could be a malfunction of Earth-made equipment, while others continue to dream that it might be evidence of intelligent life reaching out to Proxima Centauri, the closest planet outside our solar system. The possibility of encountering extraterrestrial life may not be as far-fetched as once thought. Scientists are working on shortening the time required to travel between stars, which could reduce the journey from thousands of years to just a few. Advancements in technology have even opened up the possibility of reducing travel time further, potentially making it feasible to accelerate objects to close to the speed of light. However, even with these technological leaps, reaching Proxima Centauri would still take at least 6,000 years using current methods, making it a daunting journey. The Starshot project, aimed at reaching Alpha Centauri, is considering using powerful lasers to propel small spacecraft toward their target. However, the biggest hurdle remains the interference from Earth's atmosphere, which can impact the laser's effectiveness. Laser technology can be utilized to push objects, such as paper, forward in space. Essential Maker suggests that adaptable optics could be employed in reverse to solve this challenge. Small lasers installed on satellites could continuously monitor air influences, allowing ground-based lasers to maintain a steady focus on space probes. These lasers require a massive 100 gigawatts of power to propel the spacecraft at any given moment, comparable to the entire power consumption of the United States. However, the lasers only need to operate at maximum capacity for 10 minutes to disperse the energy across a square kilometer area. To achieve this, it's expected that 100 million lasers will be used. The Starshot initiative aims to push the boundaries of space exploration. When activated, this spacecraft will reach speeds of 20% of the speed of light. The probe, which would be just over 10 meters in diameter, could reach Alpha Centauri in just 22 years. However, the gravitational pull of the Sun and interstellar debris could slow it down. Even if the probe reaches Alpha Centauri, its transmissions will take an additional 4 years to reach Earth. One of the greatest challenges is keeping the probe from slowing down. The mirror on the spacecraft must be incredibly efficient, reflecting 99.99% of the light that hits it. Additionally, it needs to double its energy transfer while minimizing power loss as quickly as possible. Once launched, the probe would travel through the Alpha Centauri system, likely never approaching any planets closely. The fascinating part of this concept is that once the setup is established, additional probes could be sent for relatively low costs. The potential of observing exoplanets, planets that orbit stars beyond our solar system, would significantly expand. In the 1990s, the discovery of exoplanets began with planets orbiting pulsars, neutron stars formed from supernova explosions. These planets, although unusual due to their harsh conditions, provided valuable insights. Later, in 1995, the first exoplanet orbiting a Sun-like star, 51 Pegasi b, was discovered. This planet, a hot Jupiter, orbits extremely close to its star. The discovery of 51 Pegasi b demonstrated that other planetary systems could exist, and they could be vastly different from our own. Since then, the search for exoplanets has rapidly expanded, aided by advancements in observational techniques. Ground-based telescopes like those at the Keck Observatory in Hawaii have played a crucial role. However, space-based observatories have significantly accelerated discovery. The Kepler Space Telescope, launched by NASA in 2009, observed over 150,000 stars and identified more than 2,600 confirmed exoplanets, along with many additional candidates. Kepler's findings revealed a surprising diversity, from small rocky worlds similar in size to Earth to giant gas planets much larger than Jupiter. The telescope showed that planets are common in our galaxy, with roughly 1 in 5 Sun-like stars hosting an Earth-sized planet in its habitable zone, the region around a star where conditions might be suitable for liquid water. Some exoplanets, like Kepler 186f, have shown particular promise for habitability. Kepler 186f is an Earth-sized planet located in the habitable zone of its star, about 500 light-years away. It receives 133% of the solar energy that Earth receives from the Sun. This discovery was a significant milestone in the search for habitable worlds beyond our solar system. Since then, several missions have built upon Kepler's legacy, including the Transiting Exoplanet Survey Satellite, TESS, launched in 2018. TESS scans nearly the entire sky to find transiting exoplanets around brighter stars, making follow-up observations easier. The James Webb Space Telescope, JWST, set to begin operations soon, will provide detailed insights into exoplanetary conditions, potentially detecting signs of habitability, or even life. The discovery of exoplanets has profound implications for our understanding of the universe. It shows that planetary systems are common and that the processes leading to the formation of Earth and other planets in our solar system are not unique. This raises the intriguing possibility that life, in some form, could exist elsewhere in the universe. As technology advances and our observational capabilities improve, the study of exoplanets will continue to be one of the most exciting and dynamic fields in cosmology, bringing us closer to answering the age-old question of whether we are alone in the universe.